Hi, welcome to the next video. So let's continue where we left off. So for the next example, we're going to find f prime of x if f of x is equal to ln of the absolute value of x. Okay, solution. First, let's point out that f of x equals ln of x is equal to ln of the absolute value of x is equal to ln of x if x is positive, and ln of negative x if x is negative. Right? And it's undefined for x equals 0. Okay, so this function is only defined for non-zero x values. Right? So the absolute value of x is x if x is positive, and the absolute value of x is negative x if x is negative. So I'll put that note here. Note the absolute value of x is equal to x if x is positive and negative x if x is negative. Now you could include x equals 0 here, but we're not using it there. So let's just think about non-zero x's. Okay? And so that's why you're replacing absolute value of x with x if x is positive, and with negative x if x is negative. Okay, so now let's find f prime of x. F prime of x, which is equal to the derivative of ln of the absolute value of x, is equal to the derivative of ln x if x is positive, which is equal to 1 over x if x is positive. Now, it's derivative of ln of absolute value of x is equal to the derivative of ln of negative x if x is negative. Well, that's 1 over negative x times the derivative of negative x, which is negative 1. And that's also 1 over x, and this is if x is negative. Okay, so the derivative, f prime of x, is equal to 1 over x if x is positive. And it's also equal to 1 over x if x is negative. Therefore, f prime of x is equal to 1 over x for all x not equal to 0. Okay? And so as a formula, you can write d dx of ln of the absolute value of x is equal to 1 over x, where x does not equal 0. That's our formula. Okay? d dx of ln of absolute value of x is 1 over x, where x not equal to 0. Okay, before when we said d dx of ln of x is 1 over x, we only had x defined for positive x values. Now, we can say ln of absolute value of x for any non-zero x. So we've enlarged the domain of our function now. Okay? The domain of ln of absolute value of x is all non-zero x's. The domain of ln of x is strictly positive x values. Okay, so now this is over all non-zero x. And d dx of ln of absolute value of x is 1 over x for non-zero x. Okay, well, that formula has a corresponding antiderivative formula. So that implies that the antiderivative of 1 over x dx, the most general antiderivative of 1 over x, is integral of 1 over x dx is equal to ln of absolute value of x plus c. And so we correspondingly get an integration formula. Integral of 1 over x dx equals ln of absolute value of x plus c. Okay? Okay, so in this example we reach this conclusion, and then we deduce that from that conclusion. Okay. So I'm going to leave the two formulas there. I'm going to erase the example where I justify that formula. Okay, so I erase the justification for this formula. We still have this formula applies that formula. Okay? So this fills the gap. In the rule for integrating functions. For integrating power functions. Okay? So the integral of x to the n dx is equal to x to the n plus first power over n plus 1 plus c if n does not equal negative 1. And so what's missing is what happens when n equals negative 1. Well, if n equals negative 1, then the integral of x to the n dx, if n equals negative 1, that integral is equal to the integral of x to negative 1 dx. That's equal to the integral of 1 over x dx. And by this formula, that equals to ln of the absolute value of x plus c. Okay, so our conclusion I'll write this out as one formula. The integral of x to the n dx is equal to x to the n plus first power over n plus 1 plus c if n does not equal negative 1, and it's equal to ln of the absolute value of x plus c if n equals negative 1. Okay, so that is the formula for the integral of x to the n dx. This implies that. That's what this implication is for here. You get that conclusion. And so now you can integrate x to the n dx. Okay, so I'll leave this up for a moment so you can copy this down. Okay, let's keep going. So example, evaluate the integral of x over x squared plus 1 dx. Okay, so to find this integral, we're going to use substitution solution. Okay, so here's the solution. I'm going to let u be the weirdest thing here in the integrand functions. The weirdest thing is the x squared plus 1 in the denominator. So u equals x, let u equal x squared plus 1, which is a fairly simple expression for u. Then du is equal to 2x dx. Right, the derivative of x squared plus 1 is 2x, and then dx. That means by the substitution rule, it's called the substitution rule, and it's also called u substitution. That means by the substitution rule, we get, so I always write this down in a very similar, I've written this down this very similar way for you each time. Okay, so let u equal x squared plus 1, then du equals 2x dx. That means by the substitution rule, we get the integral of x over x squared plus 1 dx is equal to, well, let's think integral of 1 over x squared plus 1, right? That would be 1 over u. Now, I have an x dx here, but I need a 2 there. So I asked the question, what am I missing? I'm missing a 2, so I'm going to put the 2 there. I now added a 2 here. So to fix that, I'm going to put a 1/2 in front. So I multiplied by 2 because I was missing a 2 to substitute a du in later. And then I'm going to also multiply by 1/2 to cancel the effect that multiplying by 2 had on the value of the original integral. So I have not changed the value of the original integral by multiplying by 2 on the inside and 1/2 on the outside. So that's equal to 1/2 integral of 1 over u, because that's a u. And then 2x dx is du. So it's the integral of 1 over u du. 1/2 times integral 1 over u du. And that's equal to 1/2 ln of the absolute value of u plus a constant c. You can get ln of the absolute value of u plus a constant here Then when you take the constant and add 1/2 to it, you get another constant. So I'm just skipping the algebra step there. I'm writing a plus c at the end there. Okay? And you can do that. So that equals to 1/2 ln, well, of absolute value what u is, which is x squared plus 1. And so that's the answer. So the integral of x over x squared plus 1 dx by the substitution rule is equal to 1/2 ln of the absolute value of x squared plus 1 plus c. Okay, and so that is where you're done evaluating that indefinite integral. Finding the most general antiderivative of x over x squared plus 1. Okay, there's the example. Okay, so let's do another problem. Another example, calculate the integral from 1 to e of ln x over x dx. Okay, so we're going to use your substitution again. We're going to use the substitution rule again. So solution. I'm going to write it a very similar way as before. Let u equal, and so I'm going to I'm going to use the substitution rule for definite integrals, okay? So let u be equal to the weirdest thing in this function, and that's ln of x. So let u equal ln x, then du is equal to the derivative of ln of x, which is 1 over x dx. So then du equals 1 over x dx. That means by the substitution rule, so the substitution rule in the book is named for an indefinite integral. For a definite integral, we use the substitution rule for definite integrals. Makes sense, right? For definite integrals. Okay? That means by the substitution rule for definite integrals, we get, the following. The integral from 1 to e of ln x over x dx is equal to, well, let me just separate the terms without doing anything. This is the integral from 1 to e of ln x times 1 over x dx. Right? ln of x divided by x is the same as ln of x times 1 over x dx. Okay. Well, I'm just going to write the integral sign. I'm not going to worry about the limits of integration right now. ln of x is u, so I substitute ln of x for u. 1 over x dx is du. So there we go. Now inside I have u du, so I've gotten rid of all the x's here. But now these limits of integration are values with respect to x. I need to write the corresponding values of u for these x values. So when x is 1, ln of 1 is 0. So I put a 0 here. When x is e, ln of e is 1. And so u is 1. And so now the new limits of integration are 0 and 1. So I not only rewrote this all instead of in terms of x instead of u, I also have to write the new limits of integration that correspond to these limits of integration for x. Okay, now these correspond to u. So now what's the value of this definite integral? Well, it's an antiderivative, which is u squared over 2, evaluated from 0 to 1 by the fundamental theorem of calculus or by the evaluation theorem. Okay, so you take u and you take an antiderivative, any antiderivative of u, in this case u squared over 2, and you evaluate from the lower limit of the definite integral to the upper limit of the definite integral. Okay, and then what that notation means is you take the expression u squared over 1 and you plug in the upper limit of there. So you get 1 squared over 2 minus 0 squared over 2. And that's equal to 1/2 minus 0, which is 1/2. Okay, and I added the step 1/2 minus 1/2 there. So the definite integral is equal to 1/2. Okay, and that answers the problem. Okay, the problem was calculate that definite integral, and we calculated it equals 1/2. Okay, good. Okay, so that's the solution right there. It's pretty straightforward. Don't forget, this notation is good. So when you calculate the definite integral, take an antiderivative of the integrand, put the antiderivative here, put that particular antiderivative you choose here, and then a vertical line. Put the lower limit of integration here and the upper limit of integration there. What you're saying is that the differential from 0 to 1 of u du is equal to, by the fundamental theorem of calculus, u squared over 2 evaluated from 0 to 1. Okay, one more time and slower. The definite integral from 0 to 1 of u du is equal to, by the fundamental theorem of calculus, u squared over 2 evaluated from 0 to 1. Okay? And then you take u squared over 2, you plug in 1 to it, you get 1 squared over 2 minus the same expression but plugging in 0 minus 0 squared over 2. And so you get 1 half minus 0, which is 1 half. Okay? And that's the end of the proof. Okay, so let's keep going. Next example. Calculate integral of tan x dx. There's your question, okay? Calculate the integral of indefinite integral of tan x dx. Solution. Okay, the integral of tan x dx is equal to the integral of sine x over cosine x dx, right? Tan x is sine x over cosine x. So the integral of tan x dx is equal to sine x over cosine x dx. Integral of sine x over cosine x dx. And so we're going to use u substitution here. And so we need to decide what we're going to let u be equal to. And so let's let u equal to the weirdest thing in that integrand, right? It's sine x over cosine x. So what's weirder, a sine x in the numerator or cosine x in the denominator? Let's say cosine x in the denominator is weirder. So let u equal to cosine x. Then du is equal to derivative of cosine x, which is negative sine x dx. That means by the substitution rule, we get the integral. I'm just going to write this from the beginning. Integral of tan x dx is equal to the integral of sine x over cosine x dx, and that's equal to, I'm going to separate this. This is the integral of 1 over cosine x times sine x dx, right? Sine x over cosine x is the same as 1 over cosine x times sine x. Okay, well, u is cosine x, so this 1 over cosine x is 1 over u. Sine x dx, I need a negative sine x dx. I need a negative 1 here. So what I'm missing is a negative 1. And so I'm going to say this is equal to, so you have the integral of 1 over cosine x. Now I'm going to put a negative there. I'll just put a negative 1 there. Negative 1 sine x dx. So what I was missing was a negative 1 here, so I'd get negative sine x dx and substitute to u for it here. So since I was missing a negative 1, I put it there. And to fix that, I have to multiply the outside by negative 1 also. So multiplying the inside by negative 1 to get what I wanted there, and multiplying the outside by negative 1 means that you have the same value. Okay? So now let's do u substitution. You get negative, multiplying this integral by negative 1 means it's equal to negative of that integral. So I'm going to get rid of the negative 1 and just put a negative sign there. Okay? So that's equal to the negative of the integral. 1 over cosine x is 1 over u. And negative 1 sine x dx is negative sine x dx, and that's du. So you get negative the integral of 1 over u du. Okay? Well, we had, so actually I'm going to write here, this is equal to negative the integral of negative 1, u to negative 1 du. And what that's equal to, remember we had the integral from before earlier, where I said what the integral was here. This is equal to negative ln of the absolute value of u plus c. Right? The integral of x to the negative 1 dx is ln of the absolute value of x. And so here, it's just u instead of x. And so the integral is negative ln absolute value of u, and then plus a c at the end. Well, u is cosine x. And so I'm going to substitute the u here for cosine x, and you get equal to negative ln of the absolute value of cosine x plus c. And that's the final answer. Okay, so I just substitute the u here for cosine x. And so that's equal to negative ln of the absolute value of cosine x plus c. So the final answer is that we calculate the integral of tan x dx, it's equal to negative ln of the absolute value of cosine x plus c. That's the end of that example. Okay, and so I just structured every solution using u substitution or I'm using the substitution rule or the substitution rule for definite integrals. For both of them, I structured them both very similarly. Okay, and so that's that example. Okay. So there's another way to write it. You can also write this. You can write it this way. You could also think of this as using the third law of logarithms. You could take that negative and move it here. You could have ln of the modulus absolute value of cosine x to the -1 plus c. But then that would be equal to, that's fine as an answer. This would be ln of the absolute value of 1 over cosine x plus c. But then 1 over cosine x is secant x. And so this is ln of the absolute value of secant x plus c. Same constant plus c. Yeah, we didn't change the plus c at the end. So you could either write the answer as being equal to negative ln of the absolute value of cosine x plus c, or you could write it equal to ln of the absolute value of secant x plus c. This is the added advantage of not having a negative sign in front. And so we got rid of the negative there by doing some more steps here and simplifying it so we didn't have a negative in front. Okay, but you can have a negative sign in front of the answer. Okay, and so that is the end of that example. Okay, good. So next, let's talk about logarithmic differentiation. Okay, logarithmic differentiation. So example, differentiate y equals x to the 3/4, the square root of x squared plus 1, all divided by 3x plus 2 to the 5th power. So differentiate that function. Okay, so we're going to use logarithmic differentiation for this. So I haven't said what logarithmic differentiation is yet. We're just going to do that in this example. Solution. Okay, so what I'm going to do first is I'm going to take ln of both sides. So if y equals that, ln of y is equal to ln of that entire fraction, x to the 3/4, square root of x squared plus 1, all divided by 3x plus 2 to the 5th power. Okay, ln of this fraction is equal to ln of x to the 3/4, square root of x squared plus 1, minus ln of the denominator, which is 3x plus 2 to the 5th power. Okay, and so this is by the second law of logarithms, right? Ln of a fraction is ln of the numerator minus ln of the denominator. This is equal to, now I'm going to use the first law of logarithms. It's ln of the product of two functions. Those two functions is equal to the sum of the ln's of those two functions. So ln of x to the 3/4 plus ln of, instead of the square root of x squared plus 1, I'm going to write it in exponential form. X squared plus 1 to the 1/2. And then this is minus ln of 3x plus 2 to the 5th power. Okay? Then I'm going to move the exponents in front. And so I'm using the third law of logarithms to move the 3/4 as a coefficient here. And I get 3/4 ln of x plus the 1/2 here, 1/2 ln of x squared plus 1, minus, moving the 5 in front, minus 5 ln of 3x plus 2. Okay? So what I now have is that ln of y is equal to that. Okay? I just expanded out the ln of y, or the ln of that. Okay? So first I just took ln of both sides. I got ln of y is equal to ln of that. Then I expanded this expression to write ln of y is equal to that, and this in ln of this in expanded form. Now I'm going to take the derivative of both sides. So d dx of ln of y, which is equal to 1 over y times y prime. So point out, the derivative of ln of y is 1 over y times y prime. Why is that, right? Remember before I said the derivative of ln of a function is 1 over that function times the derivative of that function. So y equals f of x is a function. So let y be that function. d dx of ln of y is equal to 1 over y times y prime, which is the derivative of that function y. So this is saying d dx of ln of y is 1 over y times y prime. And so that's what I'm writing here. Okay, well d dx of ln of y is just the derivative of that. Oh, so what is the derivative of this? It's the derivative of this plus the derivative of that minus the derivative of that. That's 3/4 times 1 over x. The derivative of 3/4 ln of x is 3/4 times 1 over x plus 1/2 times the derivative of that. That's 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, minus 5 times the derivative of ln of 3x plus 2, which is 1 over 3x plus 2, times the derivative of 3x plus 2, which is 3. And so what I found was that 1 over y times y prime is equal to that. I want to find y. The problem was differentiate y. So I want to solve for y prime. Okay? So if I want to solve for y prime, I'm going to have to erase this. The original problem was differentiate y. Okay, so I'm going to erase that. Then you can room. The goal is to learn logarithmic differentiation. So we want to differentiate y. So we want to find y prime. So 1 over y prime is equal to that. And so we're going to solve for y prime. And y prime is equal to y times all of that. 3/4 x plus 1/2 times 1 over x squared plus 1 times 2x. Minus 5 times 3 is 15. I'm just randomly simplifying things. Minus 15 times 1 over 3x plus 2. Good. Okay, and well, what's y? Y was what we had originally. So y is equal to the original expression, which is x to the 3/4 times the square root of x squared plus 1 divided by 3x plus 2 to the 5th power. That's y. Okay? That's the y here. That's y. Like in parentheses so you can see that's that. Okay? And then it's times what's already in this brackets. This is 3/4 x plus 1/2 times 2x is x. So that's x over x squared plus 1 minus 15 over 3x plus 2. All right? So the goal was to differentiate y, or find y prime, and we did. Y prime is equal to that times that, and we're done. That's the answer. We differentiated y by finding y prime. Y prime is that. Okay, and so that is the answer to that problem. And so this process is called logarithmic differentiation. Okay, first we took ln of both sides. We expanded ln of the right side. So we got ln of y is equal to this expression. That was step 2. Step 3, we took the derivative of both sides. Sorry, that's all step 1. We took ln of both sides, and we expanded this by the law of log. So this was all step 1. And step 2 was we differentiated implicitly with respect to x. So d dx of ln of y equals d dx of that. And we got 1 over y times y prime is this. That's step 2. And step 3 is we solve for y prime by multiplying both sides by y. This y times 1 over y cancels, and that y prime is equal to this times y, which is that. That's step 3. So this is step 1. That's step 1. Okay, that's step 1 in that bracket there. This is step 2. Okay, this is step 2. And then this is step 3. Okay, so those are the 3 steps of the problem. Step 1, we took ln of y, ln of both sides. Then I expanded this out, log out, and got ln of y is equal to that. That's step 1. Step 2, I differentiate implicitly with respect to y on both sides of the equation. And so ddx of ln of y is 1 over y prime, and that equals ddx of this, which is that. Okay? And then step 3, solve for y prime. So I just multiply both sides by y and got y prime is equal to y times that, which is the original y times that. Right? And the original time given y is equal to this fraction. Okay, and then that's the end. We differentiate y by finding y prime. Step 1, step 2, and step 3. Okay, so on the next board, I'm going to write the 3 steps out, what to do for each problem. But when you look back at this lesson, the 3 steps I'm about to write down correspond with 3 steps here in the solution of this problem. It's just 3 things we did in this problem. Okay? So now I'm going to write down the 3 steps. Steps in logarithmic differentiation. Steps in logarithmic differentiation. Step 1. Take natural logarithms of both sides of the equation. Take natural logs. I'm going to abbreviate for logs. Take natural logs of both sides of an equation y equals f of x, and use the laws of logarithms, abbreviated logs, laws of logs, to simplify. Okay, so step 1. Take natural logs of both sides of an equation y equals f of x, and use law of logs to simplify. Use laws of logs to simplify. 2. Differentiate implicitly with respect to x. That both sides of the equation. So after you simplify, you get y equals an expression. Differentiate both sides of that resulting equation implicitly with respect to x, meaning take ddx of both sides. And then step 3 is solve the resulting equation for y prime. Okay, then you're going to get 1 over y times y prime is equal to some long expression. Multiply both sides by y, and you'd be solving for y. So you get y prime is equal to y times some other expression, and then the original y was given to you in the problem. You can plug that expression in for y. You get y prime is equal to this f of x times something. And solving for y prime means differentiating the original function y equals f of x. Okay? These are the 3 steps. Okay? Step 1, take natural logs of both sides of an equation y equals f of x and use laws of logs to simplify. Step 2, differentiate implicitly with respect to x on both sides of the equation. Step 3, solve the resulting equation for y prime. And you're done. Those are 3 steps of logarithmic differentiation. Okay, and so that's the end of 5.2. Okay, keep going. .3. The natural exponential function. Okay, the natural exponential function. Okay, so ln is an increasing function. Is an increasing 1-to-1, that's my abbreviation for 1-to-1, is an increasing 1-to-1 function. That's my abbreviation for function. And thus has an inverse function. We call exp. Okay, so exp is the name for the inverse, for an inverse function of ln. Okay, so here is ln. I showed you the graph of y equals ln x earlier. This is the graph of y equals ln x, right? It's increasing, it's 1-to-1, it's also continuous, and so it's an increasing 1-to-1 function and thus has an inverse. And so we're going to call the inverse function exp. Okay, and so we're going to define exp. So the definition for exp is that exp of x equals y if and only if ln of y equals x. Okay, so that's how we define this function we call exp. Exp is just the inverse function of ln. Okay, so what does that mean? So let's say we have x and we have y, right? Exp is a function that maps x to y. Okay, so far not really saying anything. We're saying the input of the function is x and the output is y. Now, what the definition is, we're defining exp by being the function that satisfies this if and only if statement. And that means that if exp maps x to y, then that means ln would map y to x. So ln is going to map y to x. Okay, so we're defining exp to have this relationship with the function ln. That means exp is an inverse of the function ln. Okay, and if you graph the two graphs, you can graph the two of them. I'm going to erase this because I'm just about to rewrite it here, only larger. Okay, so I'm going to draw the same graph here. This is y equals ln x. Now if you look at the graph of y equals x, okay, y equals x, then if you take y equals ln of x and you reflect it about this line, then you get this graph. And this is the graph of y equals exp of x. I'm going to erase y equals x so because you know it's y equals x, okay? So if you take y equals ln of x in this graph, you reflect it about y equals x, you'll get y equals exp of x, right? Because when you reflect a graph about the line y equals x, the graph you get is the inverse graph. And so exp of x is the inverse of this function. And so when you flip this graph about y equals x, you get the graph of its inverse function, which is the graph of exp of x. Okay? Okay, and so this is the graph of exp of x. This is the origin 0, that's the point 1, and that's also 1. Right? If this is the point on the x-axis on the graph of y equals ln x, then when you reflect that about the line y equals x, you take the point 1, 0, and you switch its coordinates, and you get the point 0, 1. And so then the corresponding point on exp of x would be on 0, 1. It'll be 1 up on the y-axis. Okay? So that's how I know the coordinates of that point on the graph y equals exp of x. Okay. Okay, so we have the definition of exp right here. Keep going. I'm going to keep the graph on there, and I'm going to erase everything else. Okay, so notes. Exp of ln x is equal to x, and ln of exp of x is equal to x. These are the cancellation equations for exp and ln. The cancellation equations for exp and ln. But the cancellation equations just say if you compose a function as inverse, you get the identity. Or exp of ln x equals x, and ln of exp of x equals x. So those are the cancellation equations for exp and ln as inverse functions of each other. Okay. Another thing to note is that exp of 0 is equal to 1 because ln of 1 equals 0. ln of 1 is 0. Okay? And since ln of 1 is 0, then exp does the opposite, it does the reverse. And so ln maps 1 to 0, exp maps 0 to 1. So exp of 0 is 1. exp of 1 is e because ln of e is 1. Remember, e is the unique number such that ln of e is equal to 1. Okay? So we define e as being the number that ln of it is equal to 1. So ln of e is 1. exp is the inverse function of ln. So if ln maps e to 1, exp maps 1 to e. So exp of 1 is equal to e because ln of e is 1. Okay? Let R be any rational number. A rational number is a fraction. Then ln of e to the r is equal to r times ln of e by the third law of logarithms. And ln of e is 1, so this is r times 1, which is r. Okay? E to the r is equal to exp of ln of e to the r. What am I doing here? So e to the r, by the cancellation equations, I could say exp of ln of something is that something. So instead of x, write e to the r. So exp of ln of e to the r equals e to the r. exp of ln of e to the r is e to the r for that equation. Okay? So then what does that say? Well, ln of e to the r, ln and e cancel each other out, right? And so ln of e to the r is r. This is equal to exp of r. Okay? ln of e to the r is r. So then we get e to the r is equal to exp of r. Thus, e to the x is equal to exp of r. Is exp of x. So instead of r here, we just put x there. So thus exp, e to the x is equal to exp of x. Okay, so what does that imply? That implies e to the x is the inverse function of ln x, right? We let e of x is the inverse of ln. That's how we started, right? But assuming that exp was the inverse function of ln, we found that e to the x is equal to exp of x. That means that e to the x is the inverse function of ln of x. That's our conclusion. Okay? And so, another conclusion over here, that means that e to the x equals y, if and only if ln of y equals x. Because we know e to the x is the inverse function of ln x now. And so ex being the inverse of ln x means e to the x equals y, if and only if ln of y equals x. If the exponential function is 1, if this function is 1 that sends x to y, right? E to something, right? The e to something power function sends x to y. Then ln, which is the inverse of that function, will map y to x. Okay. I guess I'll put e to the x here. But it's not part of that equation. So this is called e to the x. So e to the x maps x to y, which equals e to the x. ln will then map y to x. Okay? Because they're inverses now. Okay, so we're done with that. So I'll give you a moment to look at this and write things down. Okay. Okay, so I'm going to rate this, erase this, erase this. Okay, I'm going to erase this. Okay, so in the notes I put the cancellation equations for exp and ln. But in that last board, we concluded that e to the x equals exp of x, right? E to the x is the inverse function of e to the x of ln x. So that means that we get now correspondingly, so we reach this conclusion from the earlier board and this notes. We get exp is e to the x. So e to the ln x equals x, and ln of e to the x is equal to x. And e to the ln of x equals x for x positive. And ln of e to the x equals x for all x. And so these two are the cancellation equations. For e to the x and ln x. Okay? Because now e to the x is the inverse function of exp. Okay? And so the reason why this is for only x positive is because we're plugging x into ln here. And so ln is only defined for positive x. And so we can only say this equation holds for positive x. But now this one is an x that you plug into e to the x. And e to the x is defined for any real number x. But then when you plug in, when you get the value of e to the x, you get a positive number. And so you do not need to restrict the domain at all, because e to the x is now positive, which you can plug into ln for any x, and you get x. So the domain of this is all real numbers, and the domain for this is only positive x. But these two are the cancellation equations for e to the x and ln x. Okay? And so that's that conclusion. Okay, an example. Find x if ln x equals 7. Solution. Okay, so the problem is find x if ln x equals 7. So first I'm going to write ln x equals 7. That implies that e to the ln x equals e to the 7, right? So if you make the base e and the exponents ln x and 7 respectively, they're equal, so these two are equal. But that implies, well, e to the ln x is x. So e ln x is x, right? That is that. And x is then equal to e to the 7th. And that's the answer. We found x. It's x equals e to the 7th. And we use the first cancellation equation for that. To say that, for this, say that e to the x is x, so we replace e to the ln x with x there. C to the 7th. Okay? Another example. Solve the equation. Solve the equation e to the 5 minus 3x is equal to 10. Okay? Solve the equation e to the 5 minus 3x equals 10. So, solution. E to the 5 minus 3x equals 10 is the given. Okay, that implies that ln of both sides is equal. So ln of e to the 5 minus 3x is equal to ln of 10. Okay, this is because ln is a one-to-one function. Well, no, actually, no, forget that. It's just two things are equal, so you can take ln of both of them and the same. Okay, that implies ln of e to the 5 minus 3x is 5 minus 3x, and that equals ln of 10. Right, so here, ln of e to the 5 minus 3x is 5 minus 3x, and that's from here. Ln of e to the something is that something. So ln of e to the 5 minus 3x is 5 minus 3x. So I substitute that for that by the second cancellation equation for e to the x and ln of x there. But then, therefore, 5 minus 3x is ln of 10. That implies that I'm going to move the 3x to the other side and the ln of 10 to this side. So you get 5 minus ln of 10 is equal to 3x. So I add 3x to both sides, subtract ln of 10 to both sides. 5 minus ln of 10 equals 3x. I'm going to solve for x. So x is equal to multiply each side by 1/3. Get 5 minus ln of 10 divided by 3. And that's x. And that's the final answer. And we're done with that final answer. So x is equal to 5 minus ln of 10 divided by 3. Right, so we solved the equation. Solving an equation means finding the values of the unknowns in the equation. Okay? The only unknown is x, and so solving that equation means finding the value of x. The only unknown. Okay? As a decimal, this is approximately 0.8991. Okay, so 5 minus ln of 10 over 3 is approximately 0.8991. Okay, and so that's that example. Okay, so let's keep going. Okay, properties of the natural exponential function. So, okay, properties of the natural exponential function. So the exponential function the exponential function f of x equals e to the x is an increasing continuous function with domain R and range 0, infinity. Right, and when you look at the graph of e to the x that I drew before, right, I drew e to the x, the graph of e to the x like this. This was the exponential graph, which exp of x, which was the inverse of ln x was here, exp of x was here, and e to the x is equal to exp of x. So this is the graph of y equals e to the x. Okay, it's an increasing function. It's continuous. The domain is the real line. And the range is all positive y values. So the domain is the set of all real numbers, and the range, the set of all values of the function, are all positive numbers. Because you can always find a real number, x, such that e to that x is equal to some particular positive y. And so e to the x attains a value for any positive y. So the range is 0, the open interval is 0, infinity, all positive real numbers. Okay? Thus, e to the x is positive for all x. Okay? E to the x is positive for all x. You can see that because the graph is above the x-axis, positive. Also, the limit as x approaches negative infinity of e to the x is equal to, I'm going to leave that blank, and I want you to fill that in, and the limit as x approaches infinity of e to the x is equal to blank. Okay? From this graph, right, what happens as x gets arbitrarily negative, largely negative, right? As x gets more and more negative, the graph approaches the x-axis. That means the value is approaching 0, so the limit is 0. As x approaches positive infinity, e to the x, its value is just increasing, right, to larger and larger numbers, and so the limit as x approaches infinity, e to the x is infinity, positive infinity. So that's what those two limits are. Okay? The x-axis is a horizontal asymptote of y equals dx, or f of x equals dx, of f of x equals e dx. Okay, so these are all properties of the natural exponential function. This is its graph, and these are a bunch of properties of that function. Okay, so I'll give you a moment to copy these things down. Okay, good. Another example. Find the limit as x approaches infinity of e to the 2x over e to the 2x plus 1. Okay, solution. Okay, so let's do it. The limit as x approaches infinity of e to the 2x divided by e to the 2x plus 1. Well, so I'm looking at e to the 2x and it's kind of weird. So I'm going to divide the numerator and denominator by e to the 2x. This is equal to the limit as x approaches infinity of e to the 2x divided by e to the 2x. That's divided by e to the 2x plus 1 divided by e to the 2x. Okay, so dividing the numerator and denominator by e to the 2x. And so what do you get? This is equal to the limit as x approaches infinity. E to the 2x over e to the 2x is 1. That's 1 over, well, it's 1 over this fraction. So I'm going to write the in-between step. This is e to the 2x plus 1 over e to the 2x. That's in the denominator. Okay, well, in the denominator, you have limit as x approaches infinity of 1 over. Now, this plus this divided by that, you could divide the first thing by e to the 2x and get 1. Then 1 plus 1 over e to the 2x. And see what I did here? Here there was e to the 2x here and here, but by dividing by e to the 2x in the numerator and denominator, I am now left with only one thing that's weird. So the original limit is equal to the limit as x approaches infinity of 1 divided by 1 plus 1 over e to the 2x. So the only thing that's making this, the hardest thing about this is just one fraction, 1 over e to the 2x. But let's put a note here, right? 1 over e to the 2x approaches 0 as x approaches infinity. Right? As x gets arbitrarily large, e to the 2x gets arbitrarily large. But it's 1 over an arbitrarily large number, and so that's tending to 0. So the limit as x approaches infinity of 1 over e to the 2x is 0. And so that means this is equal to 1 over 1 plus 0. Keep in mind I wrote the limit everywhere here because I had not yet calculated the limit. These steps were just algebraic, using algebra to rewrite the expression into equivalent expressions. I had not calculated the limit up to this point, and so I kept writing limit, 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 limit. Here, when I substitute this for 0, that's the reason is because I'm calculating the limit. Okay? So the reason I'm substituting this fraction for 0 is because I'm calculating the limit of that fraction. The limit of that fraction is 0. And so that's why now after this step, after this equal sign, there's now no limit, but before there was. Okay? That's because the reason for substituting here is that I'm calculating the limit. So I'm now calculating the limit, which means the limit of this thing is equal to the number 1 over 1 plus 0. Okay? And so now I get rid of the limit symbol before. Don't keep writing limit, right? You have to stop writing limit when calculating its limit. Limit of this is that number, okay? There's lots of limit laws, and so we're applying a bunch of limit laws in this one equal sign. We're saying the limit of 1 over 1 plus 1 over e to the 2x is equal to the limit of 1 divided by the limit of 1 plus 1 over e to the 2x, which is equal to 1 over, the limit of 1 is 1, 1 over the limit of 1 plus the limit of 1 over e to the 2x. The limit of 1 is 1. So you get 1 over 1 plus the limit of that, which is 0. I said that really fast. So we did limits in the past. So I just wanted to make a very quick point that when you calculate a limit and you plug something in for a number for this one part of that long expression, right? When I say the limit of 1 over 1 plus 1 over e to 2x is 1 over 1 plus 0, I'm not just directly calculating the limit of that entire fraction. I'm actually applying a lot of limit laws to say that 1 equals sign. So I don't want you to write out the steps. I just want you to be aware of the real reason why the limit of that is that. It's a little bit more complicated. It applies in maybe another board. Maybe not the whole board, but it needs some more explanation if you really explain it. Okay? But I don't want you to. So just say the limit of 1 over 1 plus that is 1 over 1 plus 0, or it just equals 1. Okay? So that equals 1, and the final answer is 1. Okay? Good? Okay, so we're going to stop the lesson here. It's a good place to stop, and we'll continue next time. Bye.